Hi there. This is a realistic DevOps interview simulation focused on scheduling, resource management, and auto-scaling in real production systems. These are the kinds of questions that test how you think about capacity, performance, and stability when workloads shift and demand changes. Before listening to each answer, pause the video and give your response out loud as if you were in an actual interview. It's the best way to sharpen your reasoning. And if you want more long-form DevOps interview simulations like this, subscribe so you don't miss the next one. Let's start with some warm-up questions. Tell me about a time you had to diagnose a resource-related issue in a production environment. A strong answer would sound like this. We had a service that looked healthy from the outside, but was slowing down under load. After digging deeper, I realized the CPU limits were too low, so the pods were being throttled heavily. Kubernetes was doing what it was told, but the configuration didn't reflect real workload behavior. We increased the limits, adjusted requests, and added better metrics so the issue wouldn't catch us off guard again. Next question. Describe a situation where auto-scaling didn't work the way you expected. A solid response would be, we had a horizontal pod autoscaler tied to CPU, but most of the bottlenecks were actually in database calls and external APIs. So even when CPU looked fine, latency skyrocketed. The autoscaler didn't trigger because the metric didn't reflect real user load. That experience taught me to pick scaling signals that match the real bottleneck, not just generic metrics. Another one. Tell me about a time when your team underestimated capacity needs. A good answer might be, during a product launch, traffic doubled overnight. We thought our cluster had enough headroom, but several workloads hit memory limits. Kubernetes started evicting pods, which only made recovery slower. After stabilizing things, we revisited our capacity planning assumptions and introduced load testing ahead of big events. Next question. How do you communicate resource or scaling issues to non-technical stakeholders? A strong response would be, I focus on impact and risk rather than internal mechanics. Instead of explaining CPU throttling or scheduler decisions, I explain how capacity affects reliability and speed. I give clear next steps and timelines so stakeholders understand what's happening without needing technical details. One more warm-up. Tell me about a mistake you made early on in managing resources or scaling. A solid answer would be, early on, I set extremely conservative resource limits because I wanted to prevent applications from overusing the cluster. But that led to constant throttling and unpredictable performance. I learned that limits are not about restricting apps. They're about giving them the resources they actually need, based on real data. Let's move into the technical section. At a high level, what does a scheduler do in a container orchestration system? A strong answer would be, the scheduler decides where workloads should run. It looks at resource requests, node conditions, taints and tolerations, affinities, and capacity. In production, good scheduling means workloads land on nodes that can actually support their requirements. Poor scheduling leads to noisy neighbors, resource contention, or pods stuck pending. Next scenario, a pod is stuck in pending. Walk me through how you debug that. A solid response would be, I check whether the pod's resource request can be met by any node. Often the requests are too high or the cluster is too fragmented. Then I look at node taints, affinities, and tolerations to see if the pod is restricted to certain nodes. Events usually tell the story, whether it's insufficient CPU, memory, or scheduling constraints preventing placement. Another question, how do you think about the trade-off between resource requests and resource limits? A strong answer would be, requests determine where pods land. Limits determine how much they can consume. If requests are too low, the scheduler may pack too many pods onto a node. If limits are too low, pods may be throttled or killed under load. The key is setting both based on real workload behavior, not guesses. Next scenario, your autoscaler is triggering frequently, but performance still isn't improving. What does that tell you? A good explanation would be, that scaling pods isn't addressing the real bottleneck. Maybe the workload is I/O bound or waiting on an external dependency. Autoscaling solves CPU and memory pressure, but it won't help if the limiting factor is serialization, downstream services, or network latency. That's when I shift focus from Kubernetes to the application architecture. Another question: how do you ensure workloads don't interfere with each other when sharing nodes? A strong response would be, I use realistic resource requests, enforce limits carefully, and employ quality of service classes. I also pay attention to node-level metrics to catch noisy neighbors early. The scheduler can only make good decisions when the inputs are accurate, so getting those numbers right is crucial. Next scenario: how do you evaluate whether a cluster is under-provisioned or simply misconfigured? A solid answer would be, I look at patterns across workloads. If everything is competing for resources, that points to under-provisioning. If only certain workloads are struggling while others are fine, it's more likely misconfiguration, like incorrect requests, limits, or affinity settings. The goal is to avoid throwing hardware at problems that are actually configuration issues. Another question: you're seeing pods get scheduled unevenly across nodes. One node is nearly full while another is barely used. How do you diagnose what's causing the imbalance? A strong answer would be, I start by looking at resource requests, because the scheduler only sees requests, not actual usage. If requests are unrealistic or inflated, the scheduler may think certain nodes are too full even when they're not. Then I check affinities, anti-affinities, taints, and tolerations to see if workloads are being constrained to specific nodes. I also review pod and node labels to make sure they still reflect the intended topology. Often, an imbalance is caused by subtle configuration drift rather than the scheduler misbehaving. Next scenario: a service is auto-scaling aggressively during peak traffic, but the newly created pods are slow to become ready. Users feel the impact before scaling catches up. What do? A solid response would be, I look at two things: signal and timing. If the autoscaler is using CPU or memory as the signal, but the real bottleneck is something else, like queue length or requests per second, it may be reacting too late. I consider switching to a more meaningful metric. Then I look at pod startup time. If new pods take too long to warm up, scaling won't help until they're ready. In that case, I work on optimizing startup, pre-pulling images, or adjusting readiness probes so pods join traffic at the right moment. Another question: a pod is being repeatedly killed, but memory usage on the node is not particularly high. What does that tell you? A strong answer would be, it tells me the pod's memory limit is being exceeded, not that the node is out of memory. Kubernetes enforces memory limits strictly. The application may be spiking above its configured limit, even if the node has free memory. I check whether the limit was set too low, whether the application has a memory leak, or whether load has increased. The key is understanding that kill is container level, not node level, unless the entire node is under pressure. Next scenario: you increase replica count for a service, but throughput barely improves. CPU usage drops slightly, but latency and errors stay high. How do you reason about that? A thoughtful response would be, the fact that CPU drops, but performance doesn't improve, tells me the service isn't CPU bound. It might be bottlenecked by a downstream dependency like a database or an external API. Adding more replicas increases concurrency, which can sometimes make the bottleneck worse by overwhelming the dependency. I'd shift focus from scaling the service to understanding what it's waiting on and whether that dependency can scale. Another question: your autoscaler scales down pods at night, but when traffic spikes in the morning, it's slow to ramp back up. Users experience slow responses during that window. What adjustments do you consider? A strong explanation would be, I look at the cooldown periods, scaling thresholds, and pod startup time. If scaling decisions take too long, I might reduce the stabilization window or adjust the target utilization so it reacts more quickly. If startup time is the problem, I work on image size, initialization logic, or pre-warming strategies. Sometimes the right answer is simply not scaling down to the absolute minimum, leaving a small baseline to handle the morning ramp. Next scenario. A team wants their workload to always run on nodes with GPUs, but occasionally pods end up running elsewhere. What do you investigate? A solid answer would be, I check node selectors, affinities, and taints. GPU nodes are typically tainted, so only pods with matching tolerations can run on them. If the toleration is missing or misconfigured, the scheduler may place the pod on a non-GPU node. I also check resource requests to see if the pod actually asked for GPU resources. If it didn't, Kubernetes has no reason to schedule it on a GPU node at all. Another question. You notice that the cluster keeps creating new pods during heavy load, but as soon as traffic drops, scaling swings back down aggressively and causes instability. How do you address that? A strong response would be, that kind of oscillation usually means the scaling policy is too sensitive. I'd increase the stabilization window, raise thresholds, or use more averaged metrics. I also look at whether scaling down is too aggressive. Sometimes keeping a slightly higher baseline is more stable than constantly reacting to micro spikes in traffic. Stability is often more important than squeezing out every bit of unused capacity. Final question for this section. How do you decide when the root cause of a resource or auto-scaling issue is Kubernetes versus the application? A mature answer would be, I look at patterns. If multiple workloads struggle at the same time or node-level metrics show consistent pressure, the issue is probably cluster-wide. If only one service is struggling while others are stable, it's usually an application-level issue, like bad limits, inefficient code paths, or dependency bottlenecks. Kubernetes rarely fails silently. When something is wrong at the platform level, the symptoms are usually broad. Let's move into the final part of this interview. These questions are intentionally ambiguous and designed to reveal how you think when systems are unstable and decisions have consequences. Here's the first scenario. Your cluster is under heavy load. Pods are being throttled, autoscaling is firing, and latency is increasing. One engineer proposes doubling all resource limits immediately. Another says the issue is clearly a downstream bottleneck and scaling won't help. You don't have full data yet. What do you do? A strong answer would sound like this. I avoid making extreme changes without understanding the direction of the problem. Doubling limits might temporarily reduce throttling, but could also starve other workloads or simply mask the real issue. Assuming a downstream dependency is the cause without evidence is also risky. I start by reducing user impact. Maybe slowing rollouts, shifting traffic, or temporarily increasing replicas, if that's safe. Then, I gather enough signal to decide whether the problem is local resource pressure or a dependency. The key is stabilizing the system without making irreversible changes. Next scenario. Auto-scaling triggered during an incident, but it actually made things worse by overloading a database. The team is frustrated and wants to disable auto-scaling entirely until they figure it out. How do you respond? A thoughtful answer would be, I acknowledge the frustration because runaway auto-scaling can absolutely make incidents worse. But disabling auto-scaling entirely is a blunt move with long-term consequences. Instead, I'd propose adjusting the scaling signal or using a safer metric that reflects real load, like queue depth or request rate. I might also set stronger limits or add circuit breakers so scaling doesn't overwhelm dependencies. Autoscaling isn't the enemy here. It's the configuration and the choice of signal. Another pressure scenario. A service is misconfigured and requesting far more CPU than it needs. This is starving other workloads. The quick fix is to lower its requests, but the service owner is pushing back, saying they need extra safety. How do you handle that under pressure? A strong response would be, I'm direct about the fact that inflated requests harm the entire system. Kubernetes scheduling is a shared resource, and fairness matters. I'd show data demonstrating the service's actual usage and explain the impact on other workloads. If they still want safety headroom, I'd negotiate a realistic buffer, something meaningful but not excessive. In pressured situations, protecting cluster stability outweighs individual team preferences. Next scenario, your autoscaler is scaling down too aggressively at night, causing slow warm-ups in the morning. Leadership wants this fixed immediately. The team proposes setting a permanent minimum replica count that doubles infrastructure cost. What do? A mature answer would be, I look for a balanced approach. A minimum replica count might help, but doubling cost permanently is probably not the best first move. I'd first examine why scaling down is so aggressive. Maybe the stabilization window is too short, or the metric threshold is too narrow. I'd also evaluate pod startup time, because improving warm-up can be more effective than holding extra replicas. If a temporary baseline is needed during high-risk hours, I consider using scheduled scaling rather than a constant high minimum. Final pressure question. During a major incident, a node becomes unhealthy and several critical pods are evicted. Some engineers want to cordon and drain the node. Others think that's too disruptive while the system is already unstable. There's no consensus. What do you decide? A strong answer would be, I look at the node's behavior. If it's consistently flapping or showing signs of deeper failure, disk pressure, network issues, or Kubernetes instability, keeping workloads on it is more dangerous than draining it. But if the symptoms are mild or tied to transient load, draining could make things worse by triggering a lot of movement at the worst time. I'd make a call based on whether the node is actively harming stability. If it is, I cordon and drain it decisively. If not, I stabilize the cluster first and revisit the node afterward. Take a moment to reflect on this interview. Scheduling, resource management, and autoscaling sound straightforward on paper, but under pressure, they become judgment calls, balancing performance, cost, and risk while the system is moving under your feet. Think about which questions pushed you the hardest and where your instincts wavered. Those pressure points are where real growth happens. Let me know in the comments which question challenged you the most. And if you want more long-form DevOps interview simulations like this, subscribe so you don't miss the next one.